Hello everyone. Today I am going to teach a few things about complex numbers, which is a topic common in many national and international curricula, grades 11 and 12 level. So, the things that we are going to learn, first we will have an intro and then we will move on to the modulus argument form. I am assuming a few prerequisites which I will mention along the way. So, let us move on to the intro where we motivate the complex numbers. What are they? Why we need them? We have seen, in fact, we are quite familiar with the natural numbers 1, 2, 3, and so on. Now, they are natural because they are quite naturally occurring. We can count using these numbers, and there are many things that we count in our everyday life. So these are the natural numbers. Now then comes the zero, which really counts nothing, and the negatives. These we call the integers or whole numbers. They might be positive or negative, but they are whole numbers. And then comes the rationals. Rational, the word ratio is included. So the rational numbers are ratios of whole numbers where the denominator is obviously non-zero. So these kind of things are rationals. 1 over 2, 1 over 3, 2 over 3, and also negatives. And the whole numbers are included. The integers are all included in the rationals. So they are there. And then comes the real numbers, where we include the rationals and irrationals. Numbers that are not quite rational, cannot be expressed as a ratio of two whole numbers. So what are some examples of those? We have seen some of those. Square root of 2, square root of 3, and maybe some cube roots, cube root of 4, and maybe numbers of the form 1 plus square root of 2, the surds. So those are all irrationals. And complex numbers are just the next step, where we can solve quadratic equations. And in fact, we can solve equations of any degree. But here we mention the quadratics because in the quadratic formula we have seen it is x equals minus b plus or minus square root of b square minus 4ac divided 2a, and this is the solution of this equation ax square plus b times x plus c equals 0. The solution is this. But often the discriminant, the thing inside the square root, b square minus 4ac, this one is less than 0. and then we have to deal with numbers of the form where there is something negative here, negative inside the square root. So that gives rise to the complex numbers. The complex numbers, let us deal with those scenarios. So that is one motivation that leads us to the complex numbers. Now I am assuming a few things here. To move on to the modulus argument form, I am assuming that the student is somewhat familiar with the forms such as this, where A is a rational real, A is a real number, B is a real number, and I is the square root of negative 1. Or we can write that I square is negative 1. I am assuming that the student is familiar with complex numbers of this form, and I am assuming a few more things. Basic knowledge of trigonometry and coordinate geometry. Now, assuming the basic knowledge of trigonometry and coordinate geometry and a little bit of familiarity with the complex numbers of this form, I will move on to the modulus argument form. Now, this is a plus bi. This is a complex number that can be represented as a point on the so-called complex plane, where this is a two-dimensional coordinate system, Cartesian coordinate system, and this is the x-axis, this here is the y-axis, and y-axis is where we put the imaginary part. That means the bi part. We put b in the y-axis, and in the x-axis we put the real part of the complex number. That means we put a in the x-axis, and then that would give us this point here as the complex number a plus bi. Now, since this is the Cartesian coordinate, we can represent the complex number in a polar coordinate system. And here I am assuming familiarity with the coordinates, the coordinate geometry. So, what is the scenario in polar? That we will see now. Now that we have this complex number, what we will do, we need to find the modulus of this complex number. What is the modulus? If we look at the representation of this complex number in the Cartesian plane, the complex plane or the Arga plane, the distance of this point from the origin, that is the modulus. That is the modulus. The distance of this point a comma b from the origin 0 and 0, that is the modulus. So what is the modulus then? Using the distance formula, the modulus is this. We take the difference between the x coordinates and square it. We sum it with the square of the difference between the y coordinates and take the square root. So this is nothing but a square plus b squared. and the square root. So this is the modulus, called the modulus. And what is the argument? If we take the modulus common, so if we write z equals, we take a square plus b square common, then what remains? A over this root over of a square plus b square remains, and bi over a square plus b square square root remains. Now this here we will write as cos of theta, and b over this we will write as sine of theta. So a over square root of a square plus b square, this is cos of theta, and b over square root of a square plus b square, that is sine of theta. And that would give us the angle theta between the x-axis and the line joining the origin and the complex number a comma b in this plane. So there we have the polar coordinates. So what are the polar coordinates here? So first we take the distance of the point, and then we take the angle that it makes with the x coordinate. And that is the modulus argument form. So what is the modulus argument form of z? So it is simply, we take the modulus in front and then cos of theta plus I times sine of theta, where the angle theta is given by these two equations. Now we will move on to some examples. So here is one example. We have this complex number minus 3 plus 3 times I, and we will represent it in the modulus argument form. So we shall call this number z, and what is the modulus of this z? So first we calculate the modulus, and that is just this. And then we need to see what are cos of theta and sine of theta, and that will give us the angle theta. So cos of theta is, we can see that it is negative. So this is minus of 1 over square root of 2, and sine of theta, we can see that it is positive. So this is just 1 over square root of 2. So sine of theta is positive and cos of theta is negative. So that puts theta in the second quadrant. And what is the angle theta? So sine of theta is this, and theta is in the second quadrant. So If theta is in the first quadrant, then sine of pi over 6 would work, but to put it in the second quadrant, we take pi minus pi over 6. And that gives us theta equals 5 pi over 6. Now, the required modulus argument form is, now in the left hand side I am writing the Cartesian form, that a plus bi form, and in the right hand side I am writing the modulus argument form. So that is where we end this small lesson. There were a lot of prerequisites, a bit of familiarity with the complex numbers, working with the complex numbers, adding, subtracting, and so on. And we needed familiarity with the basic trigonometric functions and a bit of coordinate geometry, the Cartesian coordinates and polar coordinates. That is all we need to get to the modulus argument form of complex numbers. Thank you for being there.